You've seen it everywhere, right? AI that can write, create art, even drive a car. But have you ever stopped and wondered how it actually thinks? I mean, how does a machine go from just seeing a bunch of pixels to actually recognizing a face? Well, we're going to pull back the curtain on all of it. Over the next few minutes, we're going to decode deep learning from the ground up, starting with one single artificial brain cell. Okay, first things first, let's get the lay of the land. This chart here maps it all out. Think of it like a set of those Russian nesting dolls. The biggest doll on the outside, that's artificial intelligence, or AI. That's the whole big idea of machines that can act smart. Then you open it up and you find machine learning, which is where computers learn from data instead of being explicitly programmed. And right there in the middle, at the very heart of it all, is deep learning. That's our focus. It's a superpowered kind of machine learning that uses these really cool, complicated structures called neural networks, which are basically designed to copy how our own brains work.
And that kind of brings up an obvious question. You know, the basic ideas behind this stuff have actually been around for decades. So what happened? Why is it only in the last, say, 10 or 15 years that this has just completely exploded? Well, it turns out it was a perfect storm, and this timeline shows exactly how it all came together. It really boiled down to three key things. First, starting around 2005, you had the explosion of social media. Suddenly, there was this absolute tsunami of data, pictures, posts, videos, more than anyone had ever seen. Then, around 2011, we finally got the tools, the big data technologies, to actually sort through and make sense of that mess. And the last piece of the puzzle? Pure power. From 2012 on, the computer chips you need for this, GPUs, got way, way cheaper. So you had the data, the tools to handle it, and the horsepower to process it. That was the recipe.
Okay, so to really get how this all works, we have to zoom in, like way, way in. We need to look at the single most fundamental building block of these giant artificial brains. It has a name, the perceptron. So what is a perceptron? Just think of it as one artificial brain cell. That's it. Its job is incredibly simple. All it does is take in a few pieces of information, decide how important each piece is, and then make one simple decision, a yes or a no, an on or an off. It's literally the most basic decision maker you could possibly build. In this diagram here, it might look a little technical, but it shows you that simple idea. Don't worry about the math. Just look at the flow. Over on the left, you've got your inputs. That's just the data coming in. Each piece of data travels along a line, and each line has a weight. The weight just tells the neuron how much to care about that input. We'll get back to that. Finally, everything meets in the middle, at that circle, the neuron itself. That's where the decision gets made before it sends out one single answer to the right. So, let's just walk through it. Step 1. It gathers the inputs. Let's say we're trying to predict if a student is going to pass a test. The inputs could be their IQ score and hours they studied. Step 2 is where it applies the weights. This is where it decides what's more important. Maybe hours studied is twice as important as IQ, so that gets a bigger weight. And finally, step 3, it just adds up those weighted inputs. If the total number is higher than some cutoff point, a little rule called an activation function kicks in, and the neuron fires off a pass signal. If not, it says fail. Simple as that. All right, so a simple decision maker is cute, but it's not really smart, is it? The magic, the real secret sauce of all AI, isn't just about making a decision. It's about learning from your mistakes when you get it wrong. Let's dig into that.
And this is really the most important question. What if our little perceptron predicts that the student will fail, but they actually end up passing? How does it learn from that mistake so it doesn't get it wrong next time? How does it actually get smarter?
The very first step is you have to measure just how big the mistake was. And that's the job of something called a loss function. It's really just a way of calculating a score for the error. You can think of it like a golf score. The lower, the better. If the prediction was perfect, the loss score is 0. If it was totally wrong, the loss score is huge. The entire goal of this whole learning process is to get that loss score down as low as you possibly can.
And this slide kind of shows you what's happening under the hood. Now, don't get hung up on the symbols. The idea is what's important. The network makes a prediction. We call that y-hat. The loss function's only job is to compare that guess to the real answer, which we call y. The difference between its guess and the truth, that's the error or the loss. The whole game is just a giant feedback loop trying to make that gap between y-hat and y disappear. So if the loss function is the referee shouting, "You were wrong," the optimizer is the coach that pulls it aside and says, "Okay, here's how we're going to fix it." The optimizer's job is to go all the way back to those weights we talked about, the things that control how important each input is, and just nudge them, tweak them a tiny bit, hoping to find a new setting that gives a smaller error score next time.
And this slide shows my absolute favorite way to picture how that works. It's a method called gradient descent. Just imagine that all the possible settings for the weights create a giant, hilly landscape. The height at any point is the error score. Obviously, you want to get to the very bottom of the lowest valley. So what does gradient descent do? It's like putting a ball down on the hillside. The ball checks which way is steepest, rolls a tiny bit in that direction, and then does it again and again and again, step by step, until it finally settles at the very bottom. That spot is the perfect set of weights that gives you the best answers.
Now, everything we've talked about so far has just been about one neuron, but the real power, the reason we call it deep learning, is what happens when we connect millions or even billions of these simple little guys together. And this is the main idea right here. One perceptron on its own is just a dumb little switch, but when you layer them and connect them into these massive networks, they can start to see patterns in data that are so complex, no human could ever spot them or program a computer to find them. It's this amazing emergent thing where the whole network becomes way, way smarter than any of its individual parts.
This slide shows that leap in scale perfectly. On the left, that's a simple little network, kind of like what we've been talking about. But on the right, that's a modern network used for something like recognizing objects in a photo. The complexity is just nuts, right? Layers upon layers of these neurons. But the wildest part? The basic idea is exactly the same. It's all built from those simple little pieces we just learned about. Neurons, weights, and a system for learning from mistakes. It's the scale that turns it into magic.
So let's wrap this all up and think for a second about what this all really means.
So what have we figured out? At the end of the day, even the most mind-blowing AI is built from these dead simple units called perceptrons. These things learn by making a guess, using a loss function to measure how wrong they were, and then using an optimizer to tweak their settings and try to do better. And when you connect millions of them, you get these incredibly powerful neural networks that are changing everything.
So this entire revolution is built on this really elegant, simple idea. Trial and error, just repeated millions and millions of times. These networks can already see, write, and create things we never dreamed a machine could do. And it all starts with simple parts that learn from their mistakes. Which kind of leaves us with one last huge question to think about. What will they learn to do next?